Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone and welcome to this end of term coverage for term 3, and it will be for grade 10 advanced content. I hope it is beneficial for you. Now most of this kind of term in grade 10 is centered around optics and wave optics and the physics behind light and its refraction or reflection as well as there. So we will discuss it. It's quite easy and I hope it will be nice practice for you. So let's start. Now at the beginning I would like to talk a little bit about Snell's law. What does Snell's law state? It states that if we have an object with some refractive index n1 times sine of theta 1 is equal to n2 sine theta 2. Okay, now let's try to visualize it. If we have some sort of boundary here and we have a light that is beaming here and then it refracts a little bit, and of course we have this thing here which is called the normal. Okay, it's not a very good line, let's draw something better. Okay, and we have n1 here and we have n2 here. Then this angle here, this angle is equal to theta 1 and this is equal to theta 2, and the relationship between all these four quantities is described in this kind of formula. Now what is n? N states the refractive index. It is denoted by n. It really states how much an object or some sort of medium refracts light. So the more the refractive index is, the more the bending of light is going to happen. So what is n equal to? N is equal to c divided by v, where c is the speed of light in medium and v is the velocity of that light in the new medium that we have. So we will see, for example, n in vacuum is equal to exactly 1, right? It's equal to 1 exactly. And the reason behind that is the speed of light in medium is the speed of light. It does not change, right? It's equal to c divided by c. And n in air is a little greater than the n in vacuum. So it's going to be equal to c divided by the velocity of the light in air, and it is equal to 1.00, I think another 03, right? So this is a refractive index. You don't need to memorize them, but it's good visualization. So we know that velocity of the kind of light in air is a little less than that in the vacuum. That is why the refractive index is going to be greater. Now we will solve some questions maybe later to kind of discuss it further and for us to practice. So let's talk about this very nice phenomena, very interesting one, called total internal reflection. It happens only when we have light that is going from the water medium to the air medium. So if we have kind of a boundary here and we have a beam of light that is going from this part here, which is water, and this is air. And what happens to this beam of light, if we draw the normal as well here, is that it will not refract, but it will reflect. So this is going to happen to it. So it is only one case when this happens. And if we will describe it kind of, mathematically, let's rewrite the equation. It says n1 sine theta 1 is equal to n2 sine theta 2. Of course, this is Snell's law. what will happen is the angle theta 2 is going to be quite high to the point that it's 90 degrees. So it will look something like this. N1 sine theta 1 is equal to N2 sine 90 degrees. So it's going to be 90 degrees here, right? And this is called the critical angle, because at some point here when we will have theta 1, we will have some theta 2 that is 90 degrees or more than 90 degrees. So we will not have refraction, but we will have reflection. So we have a beam of light that is going in this way. So it's 90 degrees relative to the normal. And what do we know about sine 90 degrees? We know it's equal to 1. So we have N1 sine theta 1 is equal to N2. That is why we will not have any refraction, but we will have some sort of reflection, where this angle here is also equal to theta 1. But it does not happen at every single angle. It only happens at one angle. We call it the critical angle. And the critical angle is denoted by theta c. And it will be equal to sine inverse of, let me see, because I don't remember the equation exactly, but I can derive it here. So sine inverse of N2 over N1. Alright, so this is the equation for theta c. This is the critical angle, and in this angle you will kind of understand that there is no refraction anymore, but only reflection. Okay, so this is important. It's a beautiful phenomena, to be honest, and keep in mind that it only happens when the light goes from water to air. Keep in mind that this is not the only case from water to air, but we have also other cases. But most importantly, if we call this, for example, N1 and this N2, N2 should be less than N1. This is the most important thing, that this second medium is less dense than the first medium. This is important, and we can kind of understand it if we have a look at the equation. Now, you don't have to keep this in mind if it will confuse you, but I like to kind of describe it mathematically. If N2 is greater than N1, we will have sine inverse of a number that is bigger than 1, which does not really exist, right? That's why N2 should be less than N1. Now let's describe refraction a little bit more. So if we have some sort of boundary and we have a light that is hitting this boundary and it has some angle that is theta 1 to the normal, and we know, for example, this has a refractive index N1 and this has a refractive index N2, and based on that we want to know, will it bend toward the normal or away from the normal? Let's take different cases. So the first case is going to be if we have N2 greater than N1. If N2 is greater than N1. For example, we're going from air to water, for example, so it's more dense. What will happen? So let's have a look at the equation again. We have N1 sine theta 1 is equal to N2 sine theta 2. And if we have N2 that is greater than N1, the thing that is going to happen is that theta 2 is going to decrease. That is why it will bend toward the normal. It will bend toward the normal, where we have theta 2 here. So we can say that theta 2 is less than theta 1. Okay? And the second case that we will take is if we have, let's draw it here, this time N2 is less than N1. So we have a beam of light that is hitting this boundary at some angle with respect to the normal. Let's call it theta 1. And again we have n1 and n2, but this time let's say that we have n2 to be less than n1. What will happen? The exact opposite. It will bend away from the normal. It will bend away from the normal, something like this, and this is going to be theta 2. So in this case we have theta 2 to be greater than theta 1. So the thing that we learn from this, the kind of conclusion, I will write it here, is that n is inversely proportional to the angle theta. Let's erase this one. So n is inversely proportional to theta. So the more the n, the less the angle is going to be, right? So it will bend toward the normal. But if we have a bigger refractive index, or I mean smaller refractive index, it will bend away from the normal. So keep this in mind. So let's solve these questions. As you can see here, let's have a look at the first question. The figure shows a ray of light that is PO. So this is the ray of light. Let me actually zoom in a little bit so we can see it. So this is the primary beam of light. Okay, so this is PO, and it is passing from water into air given the refractive indices of water and air. So we have N water and then we have N air. What is the correct path of the ray? Where does it go? Now I know the answer is already there, but let's prove it. So we have an angle that is 40 degrees to the boundary itself, not to the normal. Actually, let's draw it here. I will draw it again so it's clearer. Okay, so we have a boundary here and we have the ray that is hitting at 40 degrees to the boundary, and we have a normal here. And we have also the refractive indices. So we have N of water, and then we have N of air. So N of air is approximated as 1, and N of water is about 1.325. So 1.325. So using the equation, we will have to kind of understand what is the angle of basically refraction. What is the angle of refraction? So let's do it. So we have n1 sine theta 1 is equal to n2 sine theta 2. Now for theta 1, it is not 40, because 40 is the angle between the beam of light and the boundary. And to find the theta 1, we will have to get this part here. This part is 90 minus 40, and the reason behind that is because the normal, by definition, is a line perpendicular to the boundary. So 90 minus 40, which is equal to 50. So what is N1? It is going from water, so 1.325 times sine theta 1. What is theta 1? It's 50. And it's equal to N2, which is 1 times sine theta 2, which we don't know. So sine theta 2. Okay, so we will have to calculate theta 2 using the calculator, of course. So what is it going to be? Now I prefer to rearrange it, but it will be maybe confusing for you, so let's keep it like this. So 1.325 times sine 50 is equal to sine some value theta 2. Let's find it. So the calculator takes time, and the reason is because it is not rearranged properly. But what I recommend to do is rearrange it. I will do the rearranging. So theta 2 is going to be sine inverse of 1.325 times sine 50. Okay, so this is theta 2. And in the case that this is bigger than 1, if this is bigger than 1, then we will know that it is total internal reflection, therefore there will not be any angle of refraction. So let's find this case. So 1.325 times sine 50, and the answer is 1.01. Therefore, this is a total internal reflection. There will not be any refraction. Therefore, the basically angle of refraction is 0 because there is no refraction at all. So the path is going to be POW. So it's going to go something like this. If you found it confusing, we have another way to solve it. The another way is, I think, easier. It's to verify if we have total internal reflection or not. So let me remind you that the critical angle is equal to the inverse sine or the arc sine of n2 divided by n1. Okay, so what is the critical angle? Let's find it. So sine inverse of 1 divided by 1.325, and let's see what is the answer. So sine inverse of 1 divided by 1.325, and the answer is 49.0 degrees. This is the critical angle, and this angle that we have 50 is greater than the critical angle, therefore we will not have refraction, but we will have total internal reflection. So this is another way to solve it, to verify if it exceeds the critical angle or not. Now let's move to the second question. What does it say? Okay, let me raise it like this. It's actually a new program that I'm using, so I'm not sure how to use it properly, but I will get used to it. Now for the second question here, a light beam falls perpendicular to a surface and it separates two transparent medii or mediums. Their respective indices differ. Assume that nr is greater than n1. So if we have this case where we have basically a light that is shining directly perpendicular to the surface, we will have absolutely no refraction. No refraction, zero refraction. And the reason behind that is we will have n1 sine theta 1 is equal to n2 sine theta 2, while theta 1 is equal to theta 2, which is equal to 90. Right? So n1 sine 90, let's write it here actually. So n1 sine 90 is anyways equal to 0 because sine 90 is equal to 0. Therefore, since we have 0 here, we have no refraction. So there is no refraction when you shine a beam directly perpendicular to the surface. Now let's move to the next question. So let's see, what does it state? So it states a ray of light passes through a window. Which path does it take? Okay, now it seems quite confusing, but I think it's quite easy. So let me kind of zoom into the question. So it goes from air to glass, and we know that the N of the glass is higher, therefore it will be closer to the normal. And the ray that goes through the glass will be closer to the normal. Let me kind of, make the line smaller and draw a normal here. So we have here theta 1. We know that theta 2 should be smaller. So it will not go this path, but it will go this path here, because in this case theta 2 is smaller. Okay, and here, because it goes to a lower refractive index, it will bend away from this point here. That's why it will go like this. Why isn't it D? Because it turns exactly to 0. So the theta here is exactly 0, but we will not have 0. It is not possible. That is why we will have this answer here. So again, the answer is C. So we'll have challenges, therefore let's solve a challenge question. Light travels from air into another medium. The angle of incidence is 45 degrees and the angle of refraction is 27 degrees. What is the other medium? Now, a characteristic that describes a medium is basically the refractive index, n. So by finding n, we will kind of understand what the other medium is. So let me remind you that n1 sine theta 1 is equal to n2 sine theta 2. This is the equation that we have. And we just want to find one thing, which is n2. So what is n2? Let's find it. So n1 is air, so it's approximately 1 times sine of the angle 45. It's equal to n2, the thing that we don't know, times sine 27.7. And n2 is going to be equal to, let's find it. So the answer is, let's see. Now I assume that it will be bigger than 1, and indeed, yes, it's 1.52. And from the table that is provided in the book and the table that will, inshallah, be provided in the exam, we will have to kind of detect what medium has this refractive index, and based on that, we will understand the answer. So I'm not sure what is the medium, but you can, of course, check it at any time. So we discussed previously that we have n, the refractive index, and it's equal to c divided by v, which is basically the speed of light in vacuum divided by the speed of light in a specific medium. In this question, it will ask us for the speed of light in the chloroform, which has this refractive index. It has n is equal to 1.51. So we know 1.51, and it is equal to c divided by v. What is c? C is known as the speed of light in basically vacuum, and it's equal to 3 times 10 to the power of 8 meters per second, and we'll divide it by v, the value that we don't know. So v is equal to 3 times 10 power 8 divided by 1.51. And let's see what is the answer. So it's equal to 1.9, let's see, to the power of, so 1, 2, 3, 4, 5, 6, 7, 8 to the power of 8. So still a huge number. So I was scrolling around the end of term coverage or the revision for grade 10 advanced, and I found this question. It seems to be quite interesting, so let's see how we can solve it. So it says the adjacent figure shows a ray of light passing through a transparent medium if the refractive index of air is 1, and we have to calculate the refractive index of the transparent medium. So what is interesting here is, as you can see, this kind of beam is traveling vertically down the line here, the boundary, right? It goes exactly, almost exactly down. So what this means is we can assume that this angle is 90 degrees, therefore 50 is the critical angle. And what do we know about the critical angle? Theta c is equal to sine inverse of n2 divided by n1. And the nice thing here is this is satisfied because n2 air is indeed less than n1. Alright, so let's kind of calculate it. We know theta c is equal to 50 degrees. This part here, this is 50 degrees. It's equal to sine inverse of n2, which is n of air, which we assume to be 1, divided by the n of the basically transparent medium, of the medium, I will call it m. So let's just calculate it. So 50 is equal to sine inverse, so inverse sine of 1 divided by some value, which we don't know, in the calculator. I think it will take some time, so what I will do is I will multiply Oh, it did not take time. It's 1.3. So 1.31. But what I wanted to do is to manipulate this equation to, put it in the calculator and to be faster. So if I will multiply by sine in both sides, sine and sine, this will cancel out and we'll have sine 50 is equal to 1 over nm. So nm is equal to 1 over sine 50. So this is also the answer. Okay, now let's move to the lenses and let's talk about their equations. So for the focal length, it's equal to 1 over the distance of the image plus the distance, 1 over the distance of the object itself. Now to solve for f, it's just going to be the inverse of this kind of expression. Okay, and when we come and discuss the magnification, if it was greater than 1, then we know the image is enlarged. If it was less than 1, then we know it's basically reduced. And if it was 1, there is no difference at all at the image. So it is equal to h image divided by h of the object, the height basically, and it's equal to the negative basically distance of the image divided by distance of the object. And this is, or these are the equations that you really need to keep in mind. So either this one or this one, these are the exact same thing. So this is the same as this, exact. So let's move to this question. And in this question, we'll use actually both equations. So we discussed the first one is 1 over f is equal to 1 over xo or xi plus 1 over xo. And then here the other equation is the one relating the magnification. Sorry, the handwriting is not really nice. This is an I, but for speed. Okay, so the question is, where is the image? And to find the location of the image, if we know the focal length, then it is easy to find it using this equation here, right? Using this equation, we can find it. So 1 over the focal length, what is the focal length? It's 0.08, right? 0.08, because it's 8 centimeters, and 8 centimeters is just 0.08 meters, right? This is the exact same thing. So 0.08 is equal to, let's see, 1 over x of the image, which we don't know, plus 1 over x of the object. What is x of the object? It's placed 32 centimeters from the convex lens. So it's going to be 0.32. 0.32. And let's solve it. Now, if you do this in the calculator, it will take ages, to be honest. That's why I will prefer to solve it. So 1 over 0.08 minus 0.32 is equal to 1 over xi. And to solve for xi, we'll just take the inverse. So xi, this is nothing, so let me erase it. So xi is equal to 1 over 0.08 minus 1 over 0.32, all to the power of -1, and this is going to be equal to something. Let's find that something. 1 over 0.32, and the answer is 0.106. Okay, and this is in meters, of course. It's equal to 10.6 centimeters. So for the second part, where we'll solve for hi, we know ho, it's 3 centimeters, so 0.03. It's equal to negative xi. What is xi? We just solved it. It's 10.6 centimeters, or 0.106 divided by the XO, which is how much is XO? It's 0.32, basically the distance of the image. So if we solve for HI, we will get that it is, according to the calculator, so about close to 1 centimeter. To be honest, it's negative 9.9 times 10 to the negative 3 meters, which is almost like negative 1 centimeter. Okay, so this is the answer. So we know that it will get flipped, so it's flipped. So this is how we solved this question. So again, we love challenges, therefore let's solve this question, the challenge question. So a magnifier with a focal length of this much. So since we know it's a magnifier, then we're using a convex lens, but I think it's not a very important idea. But it has a focal length of 30 centimeters, and it is used to view a 1 centimeter tall object. Use a ray diagram to determine the location and size of the image when the magnifier is positioned 10 centimeters from the object. So we know the height of the object, so height of the object is equal to 0.01 meters, which is 1 centimeter, of course. And then we know that the position of the object is equal to how much? 10 centimeters, because the object is 10 centimeters away from the lens. So it's equal to 0.1 meters, which is equal to 10 centimeters. And then we have the focal length, which is equal to 30 centimeters, so 0.3 meters, which is again 30 centimeters. So can we solve it? Yeah, easily we can do it, because since we have the focal length and the XO, the distance of the object, then we can solve for the X of the image. So let me remind you again with this amazing equation. Okay, so let's substitute the numbers using another color, of course. So 1 over, what is F? 0.3. It's equal to 1 over xi. What is the x of the image? We don't know it, but we know xo, which is 1 over 0.1. It is 0.1 here. So xi is going to be equal to 1 over 0.3 minus 1 over 0.1 to the power of -1. Let's find the answer. Negative 0.15 meters. Okay, so this is the answer for xi. This is the distance of the image, and we know based on that that it is upside down, and on the other side it will be on the other side of the lens, so it's a real image. Okay, let's move now to the second part, in which we want to find the, what do we want to find? The height, I think, of the image. So use a ray diagram to location and size, yeah, size of the image, so basically the height of the image. So let me remind you that hi over ho is equal to negative xi over xo. This is the equation that we are going to use, and let's do it. So we don't know hi, but we know the height of the object. It's 1 centimeter, so 0.01 is equal to negative x of the image. We just found it, so negative 0.15 divided by xo, which is 0.1. So this is going to help us find hi. So what is hi? Let's use the calculator again. And the answer is 0.015 meters. This is the answer. So we know that it is actually reduced. It is actually reduced. It did not get bigger, it got smaller because we started by how much? We started by the height 1 centimeter, but now we see it at the height of 0.015. And it's not negative, therefore we know that it's not upside down, it is actually upright, but only smaller. Now this time we have a diverging lens, not a converging lens. So let me remind you that a divergent lens is the concave lens. So this is concave because it diverges light. But a converging lens is that of the convex, because it focuses all the light into one kind of position. So based on that, let's solve this question. We will use the exact same equations. We will not do anything different. It's the exact same thing. So a diverging lens has a focal length of 15 centimeters. So we know that f is equal to 0.15, and then that's meters, of course. A game piece placed near it forms a 2 centimeter high image. So we know that the height of the image is equal to 2 centimeters, which is 0.02 meters. At a distance of 5 centimeters from the lens. So we know that distance of the object, right? Or is it high image at a distance? So it's not XO, rather it's XI. It's 5 centimeters from the lens. What are the position and the height of the game piece? Okay, so to find the position, we will use the first equation again, which states that 1 over f is equal to 1 over xi plus 1 over xo. And the nice news, we have xi, we have f, so we can solve it. So let's replace it with a number. So 1 over f 0.15 is equal to 1 over xi, which is 0.05, plus 1 over xo, and we can solve for xo. So it's equal to 1 over 0.15 minus 1 over 0.05 to the power of -1, and let's find the answer. So it's negative 0.075 meters. This is XO. And now let's find the height, right? So let's find the height. Let me remind you again with the formula that relates the height and the positions. So HI over HO is equal to negative XI over XO. Okay, and using this equation we can solve it. So we have HI, let's substitute HI, so 0.02 divided by HO, which is the height of the object, we don't know. It's equal to negative, what is XI? We have it here, 0.05 divided by what we just solved for, so negative 0.075. Okay, and let's use our beloved calculator to solve it. And the answer is going to be 0.03 meters. So what do we learn from this kind of idea and this kind of answer, right? So basically if we look at the height of the object and we compare it to the height of the image, we will see that it was kind of reduced. Okay, so there is some sort of reduction, and the height is the same, it is not flipped or anything. And we will see that the object is at a negative, like kind of distance from the lens, and we will see that the image is at a positive distance. So we know that the image that we are seeing is virtual, it is not real.